So I'm going to introduce you to the last rule we have for speeding up finding derivatives with a function operation. So there are 5 function operations. We have add and subtract, multiply and divide. And so with derivatives, we have the sum and difference rule for add and subtract. We have the product rule for multiplying functions and the quotient rule for dividing functions. But the 5th function operation is called composition. And composition, remember, is this idea that we are sticking one function into another function. So for example, if I say the function h of x is 3x plus 1 and j of x is x squared minus x, h of j of x is an operation, that's composition, and you may have seen it as an open circle. So, and when I see the open circle, I would say composed, so this would be h composed of j of x. Well, that means that the x in h is being replaced with j of x. And then I can replace the j of x with what it's defined as. And so this would be the composition of h of j of x. Unlike adding, subtracting, or multiplying, the order of composition does matter. So if I look at j of h of x, or j composed with h of x, that means for each x that's in j, I'm replacing it with h of x. And then I can replace the h of x with what it's defined as. And here, as you can see, is a different expression when I do j composed of h rather than h composed of j. But to deal with the chain rule, we use what's called the chain rule. I'm sorry, deal with composing functions, we deal with what's called the chain rule. And I'm going to show you 2 different ways of doing this, Newton's way and Leibniz's way. I will say most people tend to prefer Newton's way, but I want to show both so you can make a decision for yourself which you prefer. So Newton's way says if we look at a composition as one function is inside of another function, we're going to find the derivative of the outside part first, and the inside does not change, and then multiply by the derivative of just the inside. So to kind of put this in perspective, this is the idea if we're going to work from our outside in. So if I have h of x is equal to 5 times 3x plus 1 raised to the 8th, 3x plus 1 is my inside. The 5 times something to the 8th is my outside. So Newton says, let's start by working from the outside in. I'm going to take the derivative of the outside. So 5 times something to the 8th means the 5 is a constant multiple. I'm just going to hold on to it. So h prime of x. 5 is a constant multiple. Hold on to it. Something raised to the 8th power means I'm going to be using the power rule. So the 8 comes down in front. My base does not change because the base does not change in the power rule. Subtract 1 to get my new exponent. But then I need to do the derivative of the inside part, and the derivative of 3x plus 1 is 3. And this gives me what h prime of x is. If I look at the same problem and decide I want to do it Leibniz's way, it's still the idea that I have f composed of g. But what Leibniz says, let's just kind of separate this idea of derivative of the outside, derivative of the inside, and not try to do it all at once. We'll do it in parts. So Leibniz says, let's first say that u is equal to whatever the inside is. And then I'm going to rewrite h of x to be, this should be an h of u. And this should be an h as well. In other words, I'm going to rewrite h of x so that it's still the function h, but it's in terms of an independent variable u and not x. So if I want to think of it that way, I would say, okay, I'm still looking for the inside. The 3x plus 1, instead of calling it the inside, I'm going to say that u is equal to 3x plus 1. So that now h of u is 5 times u to the 8th. Well, now, when I want to take the derivative of this, I'd be finding the derivative of h, and my independent variable is u, with respect to u. I can see the power rule, so I'd have 5 as constant multiple, hold on to it. 8 comes down in front, base stays the same, subtract 1 from my new exponent. But the problem is this is in terms of u, and with respect to u. I want this to be with respect to x. To do that, we sort of treat du and dx and dh as little tiny changes that we are so small that we can go ahead and cancel them as if they were the same amount of change, even though for technical reasons they're not. We just kind of pretend they are. So if I want to get dh over a dx, I need to cancel the du and have a dx on the bottom. And so to do that, I'm going to go back to my u and say, let's find the derivative of u with respect to x, which would be 3. And now together, if I have dh du and multiply by du dx, the du's cancel. And I'm using that term very, very broadly there. It's not strictly canceling, but it's an easy way of thinking about it. And will leave me with dh dx. So that means dh du was 40 u to the 7th. Du dx was 3. But then I do want to change my u's back into x's since I want to be with respect to x. So this is going to be 40 times 3x plus 1 to the 7th times 3, which is what we got doing it Newton's way as well. I will admit I'm pretty partial to doing Newton's method, so you're going to see me kind of doing that one. So kind of seeing this in action. If I want to find f prime of 1 when my function f is equal to sine of x squared plus 1, the first thing I need is f prime of x. Remember, find f prime of x, then plug the x value in. Sine is my outside. So, oops, keep my colors consistent. Sine is the outside, so I'm going to do the derivative of sine, which is cosine. The inside does not change. But then multiply by derivative of the inside, and the derivative of x squared plus 1 is 2x. And here is f prime. But then I need to plug 1 into that, so f prime of 1 will be the cosine, and 1 squared is 1, plus 1 is 2, and then 2 times 1 is 2. And without a calculator, that's as far as I can go with that. And here is the answer to our question. We then have a second example here. Chain rule is very rarely seen on its own. It's usually being done within another rule. So I'm being asked to find dh dx when h of x is x times sine of 2x. Because I'm seeing multiplication here, that means I do need to use the product rule. So for h prime of x, I have first, and then for the derivative of the second, sine is on the outside, so derivative of sine, inside does not change, times the derivative of the inside, 2, but I'm not done with my product rule yet, plus second times the derivative of the first. And here is our derivative of h.